Okay, so today we'll be solving this calculate eigenvalues of a matrix. So let's read the question. Write a Python function that calculates the eigenvalue of a 2 cross 2 matrix. The function should return a list containing the eigenvalues and sort the values from highest to lowest. Okay, so I'll be using PyTorch and it's a 2 cross 2 matrix. Return type, since it's a tensor, so we'll be returning tensor because the return type is here itself mentioned is torch.tensor, and we have to sort from high to low. Okay, so so we have a 2 cross 2 matrix and we need to find its 2 eigenvalues, right, and return them sorted from highest to lowest. So and like basically the mathematical intuition is that for a matrix, like suppose we have A and this is our input matrix 2 cross 2, and for that matrix suppose we have an eigenvalue of lambda, like for now I am taking it as L. So an eigenvalue is mostly like A times any vector is lambda times like L times V, so meaning that the matrix only scales the vector without basically rotating it. And yeah, so this is it, and the way I am thinking is eigenvalue mostly comes from solving the equation where A minus lambda L of I is where identity matrix is, like the determinant of this is 0, so 0, and which like and for, so we're just given 2 cross 2 matrix for now, so basically it will become a quadratic equation and we don't need like any iterative like numerical method, so we can just use the quadratic formula directly. So mostly like L square minus 4 of lambda plus 3 because the eigenvalues are 3 and 1, so if we have eigenvalues are 3 and the trace is 4, so itna gives us lambda as, because this will give us this for this example lambda as 3 and lambda as 1. Okay, so this, and what should be the return type? Mostly the return type is the tensor, right? So we'll just return a 1D tensor of shape 2. I'll just write here shape 2, and eigenvalues will be sorted. So one more thing for eigenvalues, like we'll ask the interviewer some questions like here, like are we guaranteed that these eigenvalues are real, because the eigenvalues can be complex, and here as we see that eigenvalues are like 3 and itna, so we'll assume that these are real eigenvalues. But like for, we could tell the interviewer that we should also note that if the discriminant, like the part under the square root of b square minus 4ac is negative, then eigenvalues can become complex. And the input type is again torch.tensor, so we'll consider, like should we consider float 32 tensor. Okay, and the input is exactly 2 cross 2, or do we need to like validate the same? So like the problem for now itself is 2 cross 2, so we'll assume 2 cross 2. So these are kind of very important questions to ask, also considering about real and no, like the complex cases. And okay, so now this will be our equation, and so and lambda, so this will come to like we can say that lambda square minus trace of A is our matrix times lambda plus determinant of A, it will be 0, and we need to find the solution of this. And the one thing to note is here this trace is coming from basically the quadratic equation, so this is basically sum of diagonals, and determinant is always like for 2, suppose we have A, B, C, D, so it will be A into D minus B into C. And in this way, if we have lambda, so it will basically, for now I'm writing T of A plus minus root of like a trace of a square plus minus root of trace of a square minus 4 times like determinant 4 times determinant of a by 2. So this comes from the quadratic equations. You can write in the, it's better to write as much as possible in your coder pad, so that the interviewer, even like sometimes they submit it to the hiring manager or something, so they would understand like you have actually how you have actually gotten through the problem. Okay, so now I think I have a clear picture, so we'll start writing. So for this we need to extract all the 4 scalar integers. As I said, like we will have a, b and c comma d. So this will be our matrix. I will take that. So a will be matrix of 0 comma 0, and then similarly b c d. So this will be 0 1 1 0 and 1 1. So these are our matrix. Now we need to compute trace. So trace will be the as I told, it will be sum of diagonals, and then we will also compute the determinant. So determinant will be a times d minus b times c. So basically, and because it is always a 2 cross 2 matrix. So and then we need discriminant, so that is also important. So we have trace, so trace into trace minus 4 into determinant, and the formula is basically trace square minus 4 into determinant of the matrix. And this is our, like for now I'm just writing it as a, and then we'll just do square root of discriminant. So since we are using PyTorch, we'll do sqrt of discriminant. So basically it will compute the square root of determinant, and this is kind of a plus minus term in that quadratic formula. And now the important part comes is like we have to there will be 2 eigenvalues, so we have to compute first. So it will be trace plus square root of discriminant by 2, and similarly we'll have lambda is, since we have plus minus, so it will be the second root. And now we have to give the, so now we have to stack the 2 scalars into kind of 1D tensor, 1D of shape tensor. So and they will already be in descending order because of plus and minus. So and lambda 1 is always greater than equal to lambda 2, because square root is generally non-negative, right? Like it's always non-negative. So now eigen values equals to torch dot stack, we can stack them together, and then lambda of lambda 1 minus and lambda 2, and we can return this eigen values. So let me submit this and check once again. Okay, so it's still running. This matrix is correct, trace is this, determinant discriminant is minus 4, determinant correct. Okay, one more thing is that one thing we could do is here is that we have this discriminant, and then we could clamp this. So this is determinant, right? So a b c d, we have trace, we have determinant, we have discriminant, and then we could also do torch dot clamp, because so discriminant and minimum equal to 0. So basically discriminant should always be greater than equal to 0, because if eigenvalues are very close, floating point error may occur. So this is done, and then I think this should be it. Let's see. our test cases are failing. So import torch calculate lambda. Oh, sorry, lambda 1 is not defined. LAMBDA. I did spelling mistake. Let's see now. And what more we can tell to the interviewer is that now for like still failing. Lambda 1 is LAM. Let's just copy paste lambda 1, lambda 2. Okay, okay, so this is all test case passing. Now now we can mention the interviewer about some of the edge cases. Okay, so the first edge case would be like if our discriminant is 0. Suppose we have 2 comma 0 and then 0 comma 2. So in this case our discriminant is 0, and so both eigenvalues is like eigenvalues is 2. So if we print the eigenvalue of 2 0 and then 0 2, so what would happen is that our clamp, because min is equals to 0, it will handle like -1 e to the power noise, right? Okay, and then the second case would be like generally with matrix, it's like identity matrix. So like 1 comma 0 and 0 comma 1. So in this case what will happen that the tray itna, and if so here determinant b1 and our discriminant will become 0, so eigenvalue will also become 1 comma 1. And we could tell more about like negative values and things like that. So and we could also run through this example of 2 comma, if we have time we could also run through example of 2 comma 1 and 1 comma 2. This is a very basic example. So our tray should be like 2 plus 2, that is 4, and basically it will be a tensor of 4.2, and determinant will be 2 into 2 minus 1 into 1, so 4 minus 1, that is 3. Discriminant will be 4 square 16 minus 4 into 3, so that is coming to 12. So 16 minus 12 is like 4.0, and clamp is 4 because max of 4 and 0 is always 4. Square root of 4 will be 2, so square root of determinant will be 2, so our lambda will be 4 plus 2 by 2, so that will come to 6 by 2 3, and lambda 2 will be like 4 minus 2 by 2, that is 1. So now we will do a stack, and stack operation of lambda 1 and L1 comma L2 will come to like 3.0 comma 1.0. And yeah, I think so this is what we could do. The other thing what we could say is like production cases, as I mentioned in all of my videos. So like in production, for batches of matrix or larger sizes, we generally use this function called PyTorch. Already gives us eigen function dot eigenvalues. So or like even for like there is eigenval sh for symmetric matrices, which is like kind of faster and like guaranteed to be, this gives a guaranteed real values. And also like these gets dispatched to fused LA pack or QSolver kernels. So I have worked with this, and QSolver is basically NVIDIA GPU like linear algebra library, and they handle like batch inputs of shape like B and M natively. So this would be the one thing. And for massive symmetric eigen problems, we have like graph Laplacians and covariance matrices that we use in principal component analysis.